First, thank the organizer for providing me the opportunity to talk about machine learning for high-energy nuclear physics. So, what is machine learning? Machine learning is a collection of algorithms that let computer learn patterns from data by themselves. Usually, people see this principal component analysis, the support vector machine, decision tree, random forest, or neural network. They are all machine learning algorithms. The keywords that are associated with this machine learning are the data-driven or parameterized functional. They are associated with the optimization. Sometimes people call it software 2.0. Because traditionally, you feed the input and the program to the computer, and the computer produces some output. And using a machine learning algorithm, actually it takes into input and output. And by optimization, it learned a parameterized function, which is a program. So that's why it's called a software 2.0. And nowadays, machine learning has been applied to many different tasks. For example, the linear and nonlinear dimensionality reduction, where people compress the data, the high dimensional data to low dimensions. Or most widely used machine learning tasks in our field is the classification and the regression. In classification, people assign labels, discrete labels to different groups of data. In regression, people assign continuous labels to different examples. And in the clustering and anomaly detection, people use the inter-particle information to classify data into different groups. And there is also a very interesting task called generation, where people train this generative adversarial network, the variation autoencoder, or flow model with many different examples. After trained, the generator actually learns statistical information from data, and it can be used to generate new examples with given conditions. For example, here, the open mouth angle actually is smoothly changing from 0 to 1. In May 2014, Atlas held a Kaggle competition. It's called Higgs Boson Machine Learning Challenge. The goal is to distinguish Higgs signal from exotic background. The winner used ensemble of neural networks. But in this competition, Qianqi Chen and Tong He, they developed XGBoost, which became the most popular machine learning tool on Kaggle. So nowadays, this boosted decision trees and deep neural network are the most frequently used machine learning tools in high-energy physics. A single decision tree is a white box model. It's a white box machine learning model where each decision process is understandable by our humans. And this decision node is chosen to maximize the information gene. One can train a more powerful machine learning tool using ensemble of trees. For example, this random forest, one actually can train many different trees in parallel. The final result is a weighted average of different trees. One can also train ensemble of trees in sequential. The second tree is trained to improve the first tree by training on the residue of the previous tree. So this is called a boosted decision tree. The Atlas actually uses this XGBoost to look for top associated Higgs. This top quark is the heaviest standard model particle that is the coupling between it with the Higgs is important for this tree level top recover coupling. The signal is TD bar Higgs, where Higgs decay to diphoton. And there are exotic background noise like TD bar diphoton without Higgs or continuous gamma and non-TD bar Higgs events. So using a boosted decision tree, they get a 4.9 significance in this TT-bar Higgs identification. In 2014, there is a very famous paper by Body. They used the deep neural network or deep learning to do this Higgs identification. So as you can see in this two process, they produce the same final state output with different intermediate stage. So one with the Higgs signal, one without Higgs. So what's interesting is that they found that a deep neural network with low-level features actually get very high prediction accuracy than a shallow neural network with even high-level features that are aided by manually constructed features. These are high-level features designed by human. So a deep neural network actually works better than a shallow neural network and this boosted decision tree. They claim that these deep learning techniques may lift these limitations by automatically discovering powerful nonlinear feature combinations and providing better discrimination power than current classifiers. So what is deep learning? To most people, deep learning stands for artificial neural network with multiple hidden layers. So this is a very simple example of a deep neural network with two hidden layers. There is one input layer where each neuron represents one pixel in the input image. In the output layer, there is one neuron to tell whether it's a cat or a dog. The value of this hidden neuron is first computed by a weighted summation of the input features plus a bias. So this Wij is the value of the links, the weight of these links. And this Zg is fed to a nonlinear activation function to produce this Hg. Without this nonlinear activation function, this is a linear model. So because there are multiple matrix multiplication equals to one matrix, so it has no representation power. With this nonlinear activation function, this neural network can approximate any continuous function. So the theta is represent all the trainable parameters like the Wij or Bj. Initially, the parameters are sampled from random numbers. So this network makes random predictions. It has to be trained. Using the network prediction and the true label, one can define a loss function as a difference between them. Afterwards, one can update the neural network parameter theta using the negative gradient of this L, the loss with regard to the network parameter. In this way, the network actually is optimized to minimize this loss function. However, in this densely connected neural network, each neuron is connected to all the neurons in its previous or in the next layer. And each link represents one trainable parameter. There are so many parameters, the network is easy to overfit. So one can require that each neuron only locally connected to several neurons in its previous layer. And further, one can ask that these neurons share weights. So these two links actually form a convolution kernel in this 1D convolution. This convolution kernel slides from up to down to produce new features. And from the densely connected to this convolution neural network, one actually reduce the number of network parameters tremendously. This two-dimensional convolution neural network is used for jet tagging, where the jet shower is represented as an image with X and Y actually are the rapidity eta and phi. And there are many different color channels represent different features of the data. And the convolution kernel here is a two-dimensional block, which slides from left to right, from top to down, to produce new features. After several convolution layers, and those neurons are flattened, and connected to a dense neural network. In the output, there are two neurons. One is a quark, one represents a quark jet, one represents a gluon jet. One problem for the convolution neural network is that we have to convert the particles into images. The particles from high-energy colliders, they are point cloud in momentum space. They have a natural data structure. So they have 4 momenta and they have PID. When people try to convert these particles into images, they actually lose information. For example, they are coarse-grained and they have lost this PID information as well. So people have tried to use the full information of the particles by using a recurrent neural network or a recursive neural network. In this recurrent neural network, all the particles are sorted by their momentum and feed to this network one after another. And in this recursive neural network, people take use of the tree structure given by this jet finding algorithm in this gluon and quark jet classification task. So each node actually takes into the information of its left child and right child and the information of itself. This is the input to the network of each node. And this is the weight matrix W. And the B is the Bayes. Sigma is the nonlinear activation function. So this network is shared among all the nodes. So it's one can also take this as a convolution for different nodes. However, this fully connected neural network, recurrent neural network, as well as this recursive neural network, all break the permutation symmetry, which means one has to sort particles in some way. There is one neural network architecture called this point cloud network, which preserves this permutation symmetry. As you can see, that there is a fully connected neural network whose input are the information of a single particle. So this rapidity phi, z, and PID is the information of a single particle. And this network produces many high-dimensional latent features, or called latent variables. And this network is shared by all the particles in a single event. So for each particle, it has a latent variable phi1. Afterwards, one uses a permutation symmetric operation, for example, like the maximum or average, to compute a new observable O1, which takes the correlation between different particles for this phi1. So afterwards, these features actually lens the correlations between different particles in high-dimensional latent space. And they are connected to a fully connected neural network and produce 2 neurons to represent the signal and the background. And what's interesting is that one can visualize what has been learned by this neural network and which region in the momentum space are most relevant for the classification task. But this particle point cloud network also has its own problem. As you can see, before this global average pooling or global max pooling, each particle is treated independently. So there is no correlation between particles. People are worried that local information or local structure are missing. So there is a new network structure called dynamical graph convolution neural network, where first people use a KNN to find the key nearest neighbor of each particle, and then compute the correlation between this pair, this xi and xj. These are their coordinates, and this fully connected neural network produces several neurons which represent the features of this link or this edge. And this convolution and this neural network is shared by all the edges. So it's called edge convolution. Finally, one not only feed the information of xi, but also the information of all the edges to the neural network. And using this way, actually, one has more local information. This idea is taken and applied in this particle net network, and using this k-nearest neighbor plus edge convolution plus point cloud network, and actually they achieve state-of-the-art classification for quark jet and the gluon jet. In this table, the first part without PID, the second part is with PID information. They both achieve this best prediction accuracy and AUC. So come back to this Heinrich-Heavian collisions. In our community, I think it's very difficult to generate data than the Heinrich physics, where they usually they use PDA. In our case, we use relativistic hydrodynamics for this quark-gluon plasma evolution, and also use transport models for this hadronic cascade. We have many model parameters that contribute to the same observable. And the question is how to constrain one physical parameter using the final state observables, and whether the information survive the dynamical evolution and encoded in final state, because there is entropy introduction, the entropy production, which means there is information loss during the dynamical evolution, and also how to decode this information from the final state particles in momentum space. So this is an inverse problem. One popular machine learning method that has used in our field is a Bayesian analysis, where we actually want to get the posterior distribution of the model parameter given the data from the prior distribution of model parameters and the likelihood between the data and the model output. This PX is evidence where one needs to integrate over the whole parameter space. It's very difficult to compute. Fortunately, we have this metropolis importance sampling that can sample unnormalized distribution without taking consider of this evidence. So it's used, this Bayesian analysis is used to constrain this QCD equation state, where the QCD equation state is parameterized as speed of sound square as a function of temperature. Without constraining, it spans a large range. And after constrained using the experimental data, it agrees with lattice QCD calculations. Another famous application is called this using the Bayesian analysis to constrain the shear and the bulk viscosity. The model is Trento plus IEB Vishnu plus ULQMD. And using this Bayesian analysis, is found clear non-zero shear and bulk viscosity. As you can see, there are clear peaks. And the blue part is given by identified particles. The red part is given by fitting the charged particles. And they still have some tension for some physical parameters. But for this eta arrest and zeta arrest, they have clear peak. And but it's not clear whether the shear viscosity over entropy density has a temperature dependence. This Bayesian analysis is also used to constrain heavy quark diffusion coefficient. When heavy quark traverses the quark-gluon plasma, its energy loss actually is sensitive to elastic scattering and this gluon radiation. And the data from STAR, ALICE, as well as CMS are used to constrain this diffusion coefficient DS. And the result is given by this red band. The lattice QCD calculations is given by these black dots. So we have also used this Bayesian analysis to constrain the jet energy loss distribution, where we formulate the jet modification factor as a convolution between the PP jet cross-section and the jet angular loss distribution function WAA. This WAA is parameterized as a gamma function with several parameters. After constrained with the experimental RAA, we found that the mean PT loss as well as this angular loss distribution function agree with this linear Boltzmann transport model for 2.7 TeV. And it describes data for lead 5 TeV, but does not agree with LBT because LBT actually uses a constant alpha S and overestimated this RAA. So in 2018, we trained a convolution neural network to classify the QCD phase transition. If we use a crossover and first order phase transition in relativistic hydrodynamics, we saw clearly separable signals for this phase transition. But if one want to tell whether this event goes through a first order phase transition from the final particles in momentum space in event by event case, it's very difficult. So we train this convolution neural network where the input is a particle spectra with 15 different transverse momentum and 48 different azimuth angles. There are two convolution layers with two fully connected layers. And we have also tried to change the number of layers and found it does not change the final results a lot. The output are two neurons to represent whether it's a crossover or a first order phase transition. We trained the model with data from Siervisk plus MPT initial condition and tested on the IEB Vishnu and Siervisk plus MP Glasma initial condition. And we get 93% prediction accuracy. So it's quite robust. Later, we have trained a point cloud network for this QCD equation state classification. In this case, we want to classify two first order phase transitions, one with a Maxwell construction, one with a spin node construction. With the spin node construction, the speed of sound square is negative, so it's unstable. And the quantum plasma will form clusters, and each blob will hadronize independently. But still, it's easy to do this classification in the coordinate space, but it's very difficult to tell whether it's a spin node or Maxwell from the final stellar particles in momentum space. And we have trained this point cloud network where we apply this 1D convolution to each single particle, where this convolution kernel actually slides over all particles to produce many features for each particle. And afterwards, we use this global max pooling to learn the correlations between different particles and using this information to produce one neuron to tell whether it's a spin node or Maxwell. Quite recently, there is an interesting paper from Fudan University where they use this autoencoder to do this nuclear liquid gas phase transition classification. So in this autoencoder, there is one neuron in the middle, which is called a latent variable. Before it, it's called an encoder. Afterwards, it's called a decoder. The network is trained to minimize the difference between the reconstructed data and the input data. It's an unsupervised learning task. The task is to reconstruct the charge weighted multiplicity for different excitations energies. And after trained, the learned latent variable actually can classify events with a low temperature from high temperature regions. So this latent variable serves as order parameter of phase transition. So it's also a very interesting study. People from Peking University actually tried to train this convolution neural network to solve this relativistic hydrodynamics, but actually it failed after the hydro evolves for 2 Fermi. And then they changed to the sticked unit, and it works pretty well. And this unit is developed originally by biomedical people to locate the tumors. And it's used here to solve this relativistic hydrodynamics as an image translation task. And it is 600 times faster than the original Vishnu 2+1. This point cloud network is also used for impact parameter determination. This neural network has been used by Stephan in 1990s to classify, to determine the impact parameter, which is the distance between, transverse distance between 2 colliding nuclei. Now here, using a point cloud network, the people from Frankfurt group, they have found that it performs much better than the traditional method, which is this polyfit given by this green line. All the other curves are from a point cloud network with different features as input or different network structures. So in our community, we did not consider the uncertainty of the neural network much, but there is a very simple way to consider the uncertainty of the network. One can, it's called the key-fold cross-validation. One can split the data into key groups and train with key-1 groups and validate on one group. In this way, one can get key validation accuracy, and the uncertainty is the standard deviation of these key models. But training deep neural network is computing intensive, so it's very difficult to get key different models. There are network structures that can naturally give the uncertainty of the model. For example, this Bayesian neural network. In the left-hand side is a traditional neural network where each link has a fixed weight. The weight are fixed numbers. On the right-hand side, it's a Bayesian neural network where each link has a distribution as its weight. So which means usually people use 2-parameter Gaussian distribution, which means people use 2 times parameters to get ensemble of neural networks. And the output is also a distribution whose variance can be used as uncertainty of the model. Another cheaper way is called the Monte Carlo dropout. One can switch on this dropout at testing stage by randomly discard some neurons and the links connected to these neurons. Using this Monte Carlo dropout, one gets different output for the same input. So the standard deviation can also be used as this uncertainty of this neural network model. A topic that is quite interesting to physicists is the interpretation, because many people think that deep neural network are black box models where we do not know what happens. There is a big field called interpretable machine learning. For example, people have already know that there is a global explanation. Using this gradient ascent, one can explain what has been learned by each neuron in the neural network. In the left-hand side, they are features learned by the neurons in the shallow layers that are close to the input layer. The patterns are very simple, just edges, corners, or color patches. On the right-hand side are patterns learned by neurons in the deep layer that are very close to the outer layer. So one can already see the object or more global information. So this kind of global explanation already tells that this neural network actually has learned layers of different representations from the data. But most importantly, one have this local explanation, which means one want to know in which region is most important for this specific classification or regression task. In this surrogate method, one can mask some piece of this input image and feed it to the network to see the prediction difference. And using that way, one can make an importance map. In this study, we actually use this activation map method to see what has been learned in this nuclear deformation prediction task. In this task, we use the elliptic flow and charge the multiplicity distribution as the input to a neural network. And the network will predict this deformation parameter beta 2. And as you can see, for this large deformation, for this beta 2, for this large deformation, actually neural network use the most central collision in this region to do this classification. But for small deformation, a neural network actually takes the information from these semi-central collisions. As a summary, so machine learning plays an important role in high-energy physics and heavy-ion collisions. And the particle net and the graph convolution neural network might be the way for the particle cloud produced in these high-energy colliders. What has not been mentioned are the PCA, the attention network, capsule network, which has been used for the jet classification. Also, there are some generators are used to do this high-dimensional numerical integration, which might be used for particle physics. There are also various applications in detector design, pair-up mitigation, and unit track reconstruction. Thank you.